Bismillahirrahmanirrahim. Assalamu alaikum. Today I am going to discuss stereoisomerism, a basic core course in BS chemistry syllabi. So what is stereoisomerism? Stereoisomerism is the type of isomerism that deals with three-dimensional shape of the molecules. Now, why is it important to study the three-dimensional shape of the molecules? One of the roles of a chemist is the design and making molecules for various purposes. For example, designing a drug molecule for a particular disease by inhibiting certain enzyme in the body. In that case, key and lock model is the best way to describe this. It is absolutely important for the chemist to make the molecules of the right shape which can sit within the cavity of the enzyme and hence inhibit its activity and stop or control the disease. The conclusion is that the molecule of the right three-dimensional shape is required. Now, in order to make the right molecule, it becomes absolutely essential to know the shape of the molecule and hence important to study this isomerism, which is called stereoisomerism. Stereoisomerism is further subdivided into three types: conformational isomerism, optical isomerism, and geometrical isomerism. Out of the three above described subdivisions, conformational isomerism arises as a result of conformational change, while the rest of the two, optical and geometrical isomerism, arise as a result of configurational change. Now, we first need to understand what configurational and conformational changes are to move further ahead. So, conformational change first. Conformational change means changing the conformation of a molecule or rotation around single bond without breaking the bonds. The conformational isomerism or conformational isomers arise as a result are called conformers. The room temperature provides sufficient energy for this change to take place, and these conformers are readily interconvertible into each other. So, they are the same molecules with different energy and stability. Some conformers are more stable than the others. The best daily life example of this conformational change is different postures of a human body, like standing position, sitting position, roll down position, or lie down position. Of course, the lie down position is the lowest energy and most stable position out of the all. So, in the same way, if we talk about simple organic molecules like ethane, then it has staggered and eclipsed conformers. The staggered one is the most stable one, and eclipsed one is the highest energy one. The energy barrier for one conformer to change to the other one in the case of ethane molecule is 12 kilojoules per mole. Now, you might be wondering what is the guide for the conversion of kilojoules per mole or with regard to rotation of the molecule. Then, as a general guide, I would just describe that 20 kilojoules per mole at room temperature provides sufficient energy for a molecule or for bonds to rotate at a rate of 2 billion times per second at room temperature, which means that they are readily interconvertible into each other. And in conclusion, bond positions, bond rotation allow molecules to adopt different conformations. Now, what configurational change is? Configurational change, as I already described, that optical and geometrical isomerism are the result of configurational change. Configurational change is a change that arises as a result of bond breaking and bond making. A different configuration is a different molecule. The change is not possible at room temperature, as room temperature does not provide sufficient energy for this change to take place. The best daily life example of configurational change are the two hands of a human body. The two hands of a human body, if you look into the mirror, one hand is a mirror image of the other hand. But if you try to superimpose the two hands one above the other, then they are not non-superimposable. As you can see, the thumb and the little finger, they have to, one little finger either has to be broken and rejoin here for the hand to superimpose onto each other. So they are non-superimposable mirror images. In the same way, the optical isomerism and geometrical isomers arise as a result of the same configurational change. The optical isomerism comes under this category where the isomers are called enantiomers, which contain chiral carbon or stereogenic centers, in which the carbon is attached to 4 different groups. The 4 different groups attached to it make it chiral carbon or stereogenic carbon. It has its mirror image, which is non-superimposable onto it. The only condition of the molecule to be chiral is having no plane of symmetry. The chiral molecule should have no plane of symmetry for its mirror image to be non-superimposable onto it. These enantiomers are identical in physical and chemical properties, and the only difference they have is rotation of plane polarized light. One isomer would rotate the plane polarized light to the right direction, while the other isomer would rotate the plane polarized light to the other direction. So due to this optical property, these isomers are known as optical isomers. The other type of the configurational change are geometrical isomers, like cis and trans forms of a double bond. These, for instance, if you have cis butene in a bottle, then on its own, it's not going to convert into trans butene over a span of time at room temperature. No. The bond has to be broken and the bond has to be remade for the trans isomer to be converted into the cis isomer. So the approximate energy required for this change is 280 kilojoules per mole, which is far, far more than what room temperature can provide. So that is another example of the configurational change. So this is a brief introduction of the stereoisomerism. In the next lecture, we will talk in detail each type of isomerism and its subsequent examples. Thank you.